So at long last, we're ready to get into the meat of the topics in this course, which is parallel programming. As with concurrent programming, we'll start with a quick overview of parallel programming concepts. And this will give you a flavor of what we're trying to achieve with all the mechanisms that Java provides that we'll talk about next. So what is parallel programming? Parallel programming is a form of computing that performs three primary phases upon, or in the context of, multiple processors and/or multiple processor cores. Nowadays, it's usually multiple processor cores, although there was a time when there were multiple processors in those days. The first phase is the split phase. And in the split phase, you take some initial task and you split it up into multiple subtasks. And we use the word fork often to describe that. You fork things up. I don't know why they call fork. It's a funny name, but that's what they're called. Ideally, when you do the forking, you want to split the task into subtasks efficiently. You don't want to have to spend a lot of time doing it. And ideally, you want to split it evenly. And you'll see in a second why we want to split it evenly. If you know much about quicksort and you know about how quicksort partitioning works best, you'll understand quickly why we want to split things evenly. And that's because you end up with a better distribution of the initial task in ways that you can run essentially evenly sized chunks in parallel on multiple cores. But I'm getting ahead of myself. So that's the split phase. And you keep doing this until some threshold is met. The second phase is the apply phase, where you take the things you split up and you run them in parallel. Now, what's interesting about this is each subtask, so the subtask that we have here, that is going to run sequentially, but all the subtasks taken together run concurrently. So it's probably too ancient a reference for most people here, but back in the day, back when I was in high school and college, Pac-Man came out. It was a really exciting video game. And you had all these little, I guess they were ghosts, and they would chase the Pac-Man, but then at some point the Pac-Man could eat them. But there was typically one Pac-Man, and later there was a Pac-Woman, but one of them, and so they would go eat the ghost at a certain point. But you have to think about, in parallel, you'd have multiple Pac people going around eating ghosts. So that's kind of the metaphor to think about. So each Pac person runs sequentially, but together they run in parallel. And then the third and final phase is the combine phase, where we're going to merge the sub-results from the processing in the subtasks into ultimately a single reduced result. And that's usually done by a process called joining. So we have forking, which is splitting, and then joining, which is reassembling and merging. And as you can see here, joining typically takes place in its own set of subphases or substeps, where you take the results from intermediate stages and you join them together until you finally end up with a final reduced result. And that final reduced result is typically either a primitive value, like an integer, or it's an object, like a string, or it's a collection, like a hash map, or a set, or a list of some kind. So that's what we do when we reduce everything to its final results. A key goal of parallel programming in general, where it be it Java or something else, Fortran, is to partition many tasks into subtasks and to combine all the results of the subtasks efficiently. Because what's the point? If you're not going to make it efficient, why go to all this trouble, right? So parallelism can thus be thought of as an optimization of key performance characteristics. So we're trying to make things run faster. And we typically want to have multiple things run faster. I always think of like a road race as an example of that. If anybody here has ever seen the classic mockumentary, This Is Spinal Tap, which you may or may not have seen, but it's a classic, funny movie. They talk about going to 11. They want to be able to make the amplifiers go to 11 because it'll be one louder. So you can think of optimization and parallelism as trying to make things go louder. There are three typical characteristics, performance characteristics we care about in the context of parallelism. The first one is throughput, which deals with how many units of information a system can process within a given amount of time. So let's say you have 5 seconds. How much throughput can you get in 5 seconds? And there's often a difference between the maximum throughput and the actual throughput. Here's a fun example from the world of computer networking to kind of make this point. So if you, when you think about bandwidth, whenever someone talks about, you have 10 megabit Ethernet or 100 megabit Ethernet or gigabit Ethernet or whatever, what they're really saying is how many things can you fit into that channel at a given point in time. And a good analogy is a road, right? So the more lanes you have, the more bandwidth you can have, the more cars you can have, unless you're in California, in which case it's just a big traffic jam 24/7. So you might have the theoretical max bandwidth, which would occur if you could have all the cars packed together like this. But of course, that would be a recipe for disaster if anything went wrong, unless you were doing some kind of chaining or platooning, I think it's called, with driverless cars. So more likely you have cars that are spread out like this. So you may get the actual throughput may be different from the max throughput. And very similar things occur at the CPU processing level, because things can't always run all the time without some costs of switching and going back and forth. Another key performance characteristic that's important in parallel programming is scalability, which is the ability of the system to handle a growing amount of workload. So as the workload goes up, you'd like the system to be able to handle it gracefully. And this is particularly something that's important with what's called auto-scaling in cloud computing environments. So in a cloud computing environment, let's say you're doing some kind of ad campaign and you expect to have lots of people come, or maybe you're YouTube and you have a particularly viral video that everybody wants to watch or whatnot. You want to be able to allocate more cores automatically in order to scale the solution to higher and higher levels of capacity and processing. And I like this little analogy because you're kind of jumping from smaller, this is auto-scaling, you're jumping from smaller configurations to bigger configurations to do more things. Now, that's what cloud computing does. We're going to talk a bit about scalability here, but usually in the context we're talking about it, you're limited by how many cores you've got on your machine, as opposed to how many cores you have in your data center or in your cloud. But the idea is still very similar. And then the third key characteristic that's important for parallel processing and parallel programming is latency, which is just the measure of the delay between when a user wants something to happen and when the system actually responds to having that thing happen. So the user wants to do something, you want to click a button, you want to make a trade, you might want to check your bank balance, you might want to transfer funds or whatever, and there's often a lag between when you initiate that and when you get the result back. Mercifully today, that lag is getting shorter and shorter, right? Because systems are getting lower latency, higher throughput, better scalability. But back in the day, it was a little slow. Minimizing latency and variation in latency, which is called jitter, is essential for mission-critical and safety-critical real-time systems. So remember those systems we talked about last time where the right answer becomes the wrong answer if it's delivered too late? That would be an example where latency really matters. And I always like to use melting clocks as an example of a non-real-time system. Time is slowing. Does anybody know who painted this famous painting? That's right, Salvador Dali. So that's the end of the overview of parallel programming concepts.